We started with creation. Why? Well, because one thing we can all agree on is that we exist. And if you don't believe that you exist, we'll talk outside of class and I'll try to convince you that you do. But once we realize that we exist and the universe is really here, we have to ask the obvious question, what? What's the logical question if you're trying to figure out your place in the universe? The universe is here, therefore, where did it come from, right? And logically speaking, again, there are only two options of where the universe came from. Option A, somebody made it, right? Option B, what? Nobody made it. Those are your only two options. Somebody made it or nobody made it. Now, if nobody made it, that means that somebody, what? Could not have made it, right? If it happened by itself, there is no creator, there is no God, and we're on our own. Option B, somebody did make it. If somebody did make it, then there is a creator, and we probably would be wise to figure out who that creator is and what they expect from us from our lives. So really what we have to do is decide, did somebody make the universe or did nobody make the universe? We started out last week by looking really at the origin of life. We went through the simplest cell that I could think of as I sat at my desk at home putting this together, an amoeba, right? That's kind of the classic textbook cell. Some scientists will probably raise their hand somewhere and say, oh, I have a simpler one. Fine, but your simple one isn't that simple, right? I don't care which cell you pick, it's not that simple. And we went through all the different pieces and parts of a cell, not so that we could all be experts in microbiology, but to realize that there's a lot more complexity there than we initially think, right? We looked at the parts, the nucleus, the food vacuole, the contractile vacuole, all the different cytoplasms and endoplasms and ectoplasms inside, how they all work together and how they're very specifically designed to do exactly what we want them to do. And science, coupled with all the best technology and research and insights that we have today, can't even reproduce one of those organelles, one of those pieces of a cell, let alone put the whole thing together. Because before you make a cell, you have to make the nucleus, you have to make the vacuoles, you have to make the cytoplasms, you have to make the membranes. We can't even duplicate one of those with our best science and technology trying to put it together. And once you create the membrane, and once you create the nucleus, and once you create the DNA, and once you create all the stuff that goes inside, then you have to figure out how to put it all together. And once you figure out how to put it all together, then you have to figure out how to make it start working, right? You don't want to just sit there with a dead cell, because what happens to dead cells? They tend not to live very long because they're dead, and they start to decompose. And so you have to make sure they're alive and reproducing and functioning and eating and respirating and all the things the cells do. How do you do all that? It's extraordinarily, I'll say extraordinarily complex. I'm not sure if that covers it or not. I like to think of the analogy of a pickup truck, and I see Steve Kurtz sitting back here. He's got some mechanical experience. Just as a hypothetical here, what would you say, Mr. Kurtz, if I would say the odds of a pickup truck forming itself because there is volcanic activity on an island, some of the heat from the rock melts some metallic alloys that happen to be present in the rock. Those alloys come together in different bits and pieces. One just so happens to form an engine block, another forms a piston, the other forms some valves and stuff. There's also some preformed organic material that got soupy and wet in that heat and that mixture, that moisture. They came together to form a serpentine belt and that and some other pulleys that happened, and they just, by tumbling and the motion of the lava running down the mountain, fit the pulleys onto the sprockets and all the timings and the belts and everything. And it came together, and the body of the truck also as well, and it all came together. Of course, it took a lot of time. Obviously, these things don't happen all in the same volcanic eruption, right? Multiple eruptions over centuries and millennia. One forms a valve, and one forms the block, and one forms the piston, etc. But eventually, all these pieces are made, and through the tumbling and wearing action of the environment and whatnot, they assemble themselves, and then finally, all the pieces come together, and an electrical spark nearby hits a tree that kind of short circuits the electrical system that is formed within the truck, and that ignites the starter, and the starter starts the engine, and the engine starts to run. Is that possible? Think about it. Given enough billions of years, is anything possible? What do you think? I know we're in the auditorium again. We've covered this. Is that possible? Are you sure? Statistically speaking, hypothetically speaking, is that possible? It kind of depends on how you define impossible, doesn't it, right? I mean, statisticians I've read, as a rule of thumb, consider impossible to be 1 times 10 to the 10th power probability. If it's less than that, they consider it statistically impossible. The likelihood of a cell forming by itself, again, according to what I've read, the numbers vary a little bit, but 1 times 10 to the hundreds and hundreds of powers. It's impossible times impossible times impossible times impossible over and over again. So, 2 problems with life evolving by itself. 1, I will restrain myself here and give them the benefit of the doubt. And instead of impossible, I'll say highly improbable, on the order of a pickup truck forming. By the way, would you agree that that's highly unlikely that a pickup truck forms out of volcanoes like that? You'd highly agree. He thinks it's pretty unlikely, right? How many things have to go wrong for this truck not to work? What if the piston is just 2 millimeters too big for the cylinder? What happens? Bad things, right? It doesn't fit all that well. Yeah. What if the boy, I'm going to take a guess here and hope not to make a fool of myself. What if the block and the pistons are made out of the wrong metal? What if they're just pure aluminum, right? And they don't have any steel or anything in them. And then the engine gets hot, and what happens to it? It tends to get soft and or melt altogether, right? Or something that rusts. It's just pure iron, and it doesn't have all the other chromium and stuff that goes into it. And then moisture gets in there, and it rusts out. What happens to the engine? It doesn't run, right? Okay. Long story short is these things take a lot of detail, just like living life does. And so to say that it came together just by chance is not realistic. If you've ever read Darwin's Origin of the Species, that's his big book that he wrote back in the mid-1800s, 1850s is when that came together. If you've ever read that, he talks about kind of things he's observed and why he thinks that evolution may be true. And not to give him an excuse, but he did live in the mid-1800s, right? I mean, knowledge back then wasn't quite what it is today. And he had a theory called his little black box theory. That is, we can't really see at this point inside of cells or what makes them work or how information is passed from one generation to the next, right? He believed that if a trait that the parents used and developed in their generation would be passed on to the offspring. In other words, if I go running every day and build up leg muscles and lung capacity, my children are more likely to have stronger legs and greater lung capacity. And if they run every day and build up their tolerance even more, their kids are more likely to have even bigger lung capacity and stronger legs. And so over the generations, these traits that get used from generation to generation, passed on to the following generation, eventually you will come up with an entirely new type of species or type of animals, right? Of course, he didn't use the analogy of running. He talked about parakeets, and he talked about tortoises and giraffes, right? The horses that have to stretch up to get the leaves on the trees, and so they don't starve when the drought comes. Those ones that stretch are going to have children that tend to have longer necks. And those animals will have to stretch, and their kids will have to stretch. And so eventually, you go from a horse to a what? A giraffe. That's one of the examples he uses, sure. Now today, we know a little bit more about genetics, right? Of course, he didn't at that time. Incidentally, about the same time that Darwin was writing his book, there was another guy called Gregor Mendel, and he started his work with genetics on pea plants over in a monastery elsewhere. But of course, he didn't know that at the time. So while one guy was actually studying genetics, Darwin was saying that traits are passed on just by use from one generation to the other. Where was I even going with all this? I don't even remember anymore. Anyway, it just doesn't work that way. But he had a theory called the black box. That is, if you look into the details of life, things that we don't understand right now, but as we probe further and further, you're going to finally get to a point where everything is extraordinarily simple. We don't know how cells work, and we don't know how organisms function together and how the tissues and all that, or genetics or anything that works. But someday we will zero in and we'll learn enough that everything just kind of becomes very simple. It just kind of works itself out. Of course, we know again today, 170 years later, that quite the opposite is true, right? The more we learn, the more detail we find out, and the more complex things become. And so what to Darwin, he hoped cells, once you open them up, would become extraordinarily simple. We now know that they are extraordinarily, what? complex. Yeah, complicated. And genetics, it's not as easy as just I stretch out my neck and so my kid will have a longer neck. Genetics is DNA and it's RNA and it's messenger, codons and genes and cells and chromosomes and all this extraordinary double helix stuff that goes on. Very complex stuff that can't just happen by itself. It doesn't just organize itself and pop out. It's not like little tiny dots of jelly all over and that becomes a cell. It's way, way more complex than that. So, origin of life, two problems. One, it's highly improbable. Again, I'm trying hard not to say impossible yet. If it's simple enough to have happened randomly in a puddle, why don't they replicate it in a laboratory? In other words, if in the textbooks they will tell us that cells can happen by themselves over millions of years accidentally, it should be pretty simple stuff to intentionally do it in a laboratory. And yet we cannot. We can't even design the first part of a cell, let alone all the parts of a cell, and then put them together and then bring them to life. We can't do it. And even if at some point we could, all that would prove is that it takes extraordinary technology and a lot of intelligent design to reproduce it, which is what we're saying happened the first time all along. But there's another situation, even given millions of years where one part forms and then a couple million years later through chance and random activation another part of the cell forms and finally it all comes together. Years ago, I used to work in a laboratory that dealt a lot with enzymes. Enzymes are just fancy proteins that help other reactions take place, within a cell and within living beings. And whether I should have or not, I did photocopy a page out of one of the test procedures that we used for enzymes. Here it is. We are not going to go through all this. You don't care how to make acetate buffers and all that kind of thing. But there's one phrase in here I want you to kind of zero in on, and I want you to think about the implications of what you're seeing. You see that center section there that says enzyme preparation? Let me zoom in on that a little bit. And I've highlighted one line. That line says, all enzyme solutions must be used or tested within 30 minutes of preparation as they tend to, what's that word? As they tend to degrade. The problem with great big organic molecules that make up cells is that they are not very stable. If you expose them to oxygen, if you expose them to UV radiation, they just heat, they tend to break down very easily. Now apply this in the formation of a cell. Even if we, against all odds, happen to create a nucleus in 1 century, and then 1,000 years later, we'll speed things up, right? Even if it doesn't take millions of years, if it takes 1,000 years, and then we make a vacuole, and then 1,000 years later, we create a membrane. What happened to the things that we created 1,000 and 2,000 years ago? They are long gone. How long did this assay give before the assay is considered invalid because things have broken down so badly? How long do we have? 30 minutes. Now, if you're a cell trying to form randomly in a puddle on ancient Earth, how long do you have to form from start to finish before you have to be a living, functioning cell or you start to degrade? How long do you have? Years? Months? Weeks? Hours? You don't have very long, because start to finish, all the parts that you randomly do form against all odds, which are impossible to form anyway. But even if you did form them, you have a very limited amount of time before you better be a functioning cell, or else what you created will start to come apart again. To the evolutionist, a lot of time is your best friend because you can increase your odds, right? Given enough time, anything can happen. Unless everything you tried to do a week ago is already disintegrated today, right? All of a sudden, time is not your friend anymore. It becomes the enemy. So, first problem is it's highly improbable to happen in the first place. Second of all, it's completely impossible because complex organic material is not stable. It degrades very quickly. So the evolutionists will have to come up with a reason and an explanation on how cells went from zero to living in a very short period of time, and it can't be done. Just for fun, I found this article. This is a couple years old, Nature magazine on the internet, International Weekly Journal of Science. This is not a Christian organization. In fact, during this class, I like to use non-Christian sources just to show you from their own mouths that this is impossible, right? If I prove evolution, or if I prove creation by giving you creationist sites, you'll say what? Well, of course that's what they're going to say because they're creationists. But if I show you evidence from secular sites, maybe it's a little more meaningful. But look at this title here. If you can read it, I know the print is small. I apologize. Minimal Cell Raises Stakes in Race to Harness Synthetic Life. This is a guy who said, I'm going to set out and I'm going to create a synthetic cell to show that it can be done. And I'm not trying to put this guy down. He's clearly a brilliant guy, highly technical. His achievements are honestly impressive. I mean, he did good work here. But think about some of the things that he says, and I've highlighted throughout the article just a few clips. We'll not read the whole thing. Genomics entrepreneur Craig Venter has created a synthetic cell that contains the smallest genome cytogenetics, of any known independent organism. Functioning with 473 genes, the cell is a milestone in his team's 20-year quest to reduce life to its bare essentials and, by extension, to design life from scratch. So he said, I'm going to start out and I'm going to create my own living cell from scratch to show that it can be done. I'm going to start with a very base minimum, most simple cell I can come up with, and here's my report. It took me, how long? 20 years of intense research and intelligent design to put it together. But here's what we found. Continuing on, the next yellow section up there. The design and synthesis of genomics from scratch remains a niche pursuit. It's technically demanding. In other words, even in a laboratory with the most brilliant minds you can find, it's extraordinarily difficult and time-consuming. By contrast, the use of genome editing is soaring, and its most famous tool is this CRISPR-9 program and stuff, and it goes along to talk about it. But it says, creating things from scratch is extraordinarily difficult, so it's much easier to take bits and pieces of what already exists and mix and splice them together. Okay, I totally understand that, but now you're not creating from scratch anymore. Okay? Continue on. He says, the effort required in the development of new technologies is very difficult, but by 2008 they had used this method to make what was essentially an exact copy of the, and there's that cell genome, that also included dozens of non-functional snippets of DNA watermarks. So he says, we are going to copy the bits and pieces that we want from another cell that already exists. Again, I totally respect that. I mean, how do you start from scratch? But again, you're not creating from scratch anymore, right? Continuing on. Next page. With nearly all of its nutrients supplied through growth media, in other words, what this guy did is he took out all the genes that he could. He said, normal cells have to produce some of their own nutrients internally to function. We're going to remove all that so that on its own it can't really live, but I will artificially supply everything it needs to live just so I can simplify it enough so that I can do it. So he did all that. With all that removed, the essential genes tended to be those involved in cellular chores, such as making proteins, copying DNA, and other stuff. But he says, astoundingly, he says that his team could not identify the function of 149 of the gene's genome, many of which are found in other life forms, including humans. He said, we don't know about a third of essential life, and we are trying to sort that out now, he says. And I read that and I thought, wait a minute, I thought you just synthesized and put all this together. How can you put it all together if you don't even know what it does? Well, again, he took bits and pieces, took out what he thought was essential, and he said there's still a bunch of stuff here that is necessary for life because our other trials died, but we're not quite sure what it does yet. It's so complex. Continuing on, the sluggish growth of the natural, and there's the kind of cell he used, prompted him to switch to the more prolific, and there's another kind of microbe, another kind of cell. This time they not only synthesized its genome and watermarked it with their names and other stuff, but also implanted it into another bacterium that had been emptied of its own genome. So what they were able to do is not quite create life from scratch the way the title led you to believe. What they did was they took bits and pieces of existing DNA, they spliced it together as best they could and modified it down to its barest form. They still couldn't figure out about a third of what it did, but they knew it had to be there or else the cell died. And then they took those genetics that they created, but they had no cell to make it live, and genes without a cell to live in decompose very quickly. So they had to take another existing cell, rip out the genetic guts, and put their stuff into the cell so that it would survive. Now again, am I putting this guy down for being stupid? Not at all. I couldn't do this stuff. It's brilliant work. It really is. But it only demonstrates that they couldn't create their own cell, they couldn't make it from scratch, and they don't know a third of what it does, even with the most brilliant minds and the best technology our world has to offer. Again, I ask, is this something that could really happen on its own randomly in a puddle, truly from scratch with no help? I really don't think so. I just don't think that that is a reasonable faith to believe. And again, if you are an evolutionist, unfortunately, that's what you have to subscribe to. You have to say, yes, I think all this complexity could happen even though it's impossible. Natural law says impossible, but I'm going to believe it anyway. Everybody say, whew. Yes, thank you, that was complicated. Let's move on. I'm tired of cells, aren't you? Let's go from the small stuff to the big stuff. And again, I'm not trying to just bury us all in technical data here. I'm trying to explode our minds, realizing how complicated God's creation is. Let's go to the big stuff, the solar system. Here's another article I found from SciTech on Fox News by Ray Villard on September 28, 2011. Was a giant planet ejected from our solar system? Was there another huge planet going around our sun in our solar system that got kicked out and is now meandering its way aimlessly across the universe? The obvious question you'd ask is, I see some of the expressions, what's the question? Why would you think that, right? What leads you to think that? Well, let's figure it out. The very bottom line there, I didn't highlight it, but it says, a new set of computer simulations suggests that there was once a fifth giant planet in addition to Jupiter, Saturn, Uranus, and Neptune. Besides all the big planets we have, a computer simulation says there had to have been another planet here. That sounds pretty convincing, doesn't it? What makes the computer simulation think that? Computer simulations, by the way, just an aside here, only know what you tell them. And all the assumptions that you put into it is what is going to spit back out at you. Okay, just a little technical insight there. Continuing on, the fifth planet sounds like a great name for a sci-fi movie. But the fifth planet may be real, a hypothesized giant world that was flung out of our solar system 4 billion years ago. It would have drifted tens of thousands of light years away by now. Why even suspect that such a planet existed? Hey, good question. That's what I just asked too. Let's find out. Though astronomers have found many planetary systems around neighboring stars, our own solar system looks like it's the exception rather than the rule. Our solar system here is very weird. It's unusual, he says. We're discovering that our system is an uncommonly orderly place, where the planets behave themselves in wide orbits that are nearly circular. He says our solar system is very calm, very ordered, very organized, very circular. We'll talk about that in just a minute. He goes on to say, the planetary systems around other stars found so far present a sort of wild west of planets. Their orbits can be steeply inclined to one another. Our 8 major planets are very coplanar. That means they don't interact and interfere with each other. Everything is very predictable, very stable, very safe, and very orderly. There are many giant planets that have migrated precariously close to their stars. Other planets are in roller coaster, highly elliptical orbits that alternatively freeze and cook them. In other words, most planets around most stars are more egg-shaped than round, right? And they get close to their stars and far away, and one planet goes like this, and one planet goes like that. And you know how if things intersect, what tends to happen from time to time, right? Down in Awana, we tend to run, what do we call it, the figure 8 race? Is that what they call it? Right. And that's where we have 2 circles, and we have the teams run around the circle this way and back across the other circle the other way to form a figure 8. And all 4 teams are doing this at one time. And that's such a fun game because why? There's one specific spot on this track that's of particular interest. Do you know which spot that is? Yeah, that's what makes the game fun. At one spot, the 2 paths, what? They cross. And every now and then, if it's a really good night, you can have a runner coming this way and a runner coming this way. They're going to be focused on running, not looking side to side, and what happens? One of 2 things, right? If it's a really good night, we have BAM! And the 2 kids fall over and they go, wow! And it's really fun, and everybody gets a good laugh except for those 2 kids. If you're watching on the internet, you have to know my humor. I'm sorry. We don't really laugh at kids hurting themselves. On the outside. In the inside, we do. On a really good night, you have 2 kids collide, and they just absolutely hurt themselves and fall over in a bloody mess. If it's a medium good night, they just come really close, and they scare each other. Ooh, that was a close one. Wow, you know. That's what happens in many planetary systems around the suns. One planet goes this way, one planet goes this way, and eventually either 1 of 2 things happen. Unlikely, but it can happen that the 2 planets actually collide. Or if they get even close enough to each other, the gravity of this one messes with the gravity of that one, and they kind of throw each other off of their tracks, and now they're going in a different direction or a different speed or a different distance. And of course what that does to the world is it changes the whole ecology and the climate and all that kind of thing. And things either tend to freeze because the planet gets moved out, or they cook because it gets moved in. It's just chaotic mess. But our solar system is really, really weird. Super weird, in fact. Because for some reason, our planets don't intersect. They all go around in the same plane. They don't interact with each other. If one went this way, one went that way, and Earth came too close to Jupiter or something like that, or, what am I trying to say? You know what I mean, the paths cross or become close to crossing, and it would really mess with us. You talk about climate change due to burning fossil fuels, which is a whole other debate. Imagine what would happen to our environment and our climate if we got kicked by another planet half again closer to the sun. We would all be what? Dead. Yes. Yeah, we'd all be dead. But our solar system doesn't do that. Even more befuddling, he continues, confusing. It's hard for theoreticians to build planet formation models that winds up looking like our solar system. Assuming we have a randomly organized solar system, our computer models and our theoreticians, our smart people, can't even figure out how our solar system could have come to be the way that it is. It's too organized, it's too peaceful, it's too ideal. It just doesn't work that way. So we have to come up with a reason. First reason that it was organized and designed that way is unacceptable, because that would demand the existence of a what? Creator. That's not acceptable. We have to come up with another reason. So the reason is a new set of computer simulations by David Desvourny, sorry David if I messed up your name, of Southwest Research Institute in Boulder, Colorado, shows that this will work. We can create our solar system the way it is if there was once a fifth giant planet in addition to these other planets. Aha! That's why they have to create another hypothetical planet. Now we understand. Because the way that our solar system is now could not have happened by chance with all the existing players. We have to introduce something else to change it, to fix it in a way that we now see it. He continues on talking about different planets and stuff. We're going to fast forward. We don't care about that as much. Looking for evidence of a fifth planet calls for solar system forensics. We need to figure out how this happened. God didn't leave behind any file footage of the solar system's formative years after all. Ha, ha, ha. And we're laughing at the existence of God here, right? Incidentally, by the way, he did leave file footage. It's not video footage, but it is verbal footage. You can find it in Genesis chapter 1. First, it is known that Uranus and Neptune are too far from the sun for them to have formed in their present locations. In other words, where they are and how they're put together is impossible. They cannot be there the way they formed. Something else had to have happened. We have to find a way to explain this. There simply has not been enough time and materials for them to agglomerate, to come together into the size 15 Earth masses that they are. These two planets must have formed closer to the sun and then migrated outward. They can't exist where they exist, and yet they do. So they had to have formed somewhere else, and then something else had to push them out to where they are to explain their existence. This implies that the early solar system was very chaotic. Smaller bodies, the planetesimals, the little planets, were gravitationally kicked around, and the exchange of momentum widened the orbits of the outer planets. Our moon bears the scars of this rough and tumble period about 4 billion years ago. So what he says is, aha, our system is so organized, clearly another planet had to have been whirling around, taken in a chaotic, wild way, taken all these other wild, chaotic planets, manipulated them in just the perfect way so that the mystery planet got ejected out and left everything else in perfect, calm order. Right? Because we all know that that's how it works. The more chaos you introduce to a system, the more orderly it becomes. Right? And so it starts out really wacky and wonky, and planets are flying everywhere, and this one's getting kicked, and that one's getting kicked, and this one's getting moved. Finally, the intruder gets shot out into the universe, and what's left? A perfectly orderly, peaceful solar system. How does that sit with you? Everybody good? I see some heads shaking. You don't seem to buy that. But that's what the computer simulation says. Why would you disagree? Come on, why would you disagree? Because the simulation only knows what you put into it. And so if I reverse engineer the solar system we have, and I put everything in just the right place, and add a mystery planet to help it all take place, and back calculate it so that the end result will be what I want it to be, a peaceful, ordinary system that we have, guess what? In the computer model land, it works. But your starting point took as much design as the finished product did to make it work. But if you don't have that weird rogue planet kicking things around, what are you left with? You're left with a perfectly organized solar system, ideally designed for life, that you can't explain unless you introduce a creator to make it work. And as I already said, the creator is an unacceptable option. So, let's take a look at our solar system. Distance from the sun. If our Earth is too close to the sun, what happens? We cook. We die, right? The oceans boil off, or even if they don't boil off, what happens if the average daytime temperature shoots up to, say, 150 degrees Fahrenheit? What happens? We die, right? If it goes too far from the sun, things cool off, the oceans freeze, and pretty soon we what? We die. So that's important. Everybody just heard of the Goldilocks Zone, right? If you follow exoplanet stuff at all, you know there's a certain distance, a certain range from a star that the planets have to be in order to be the right temperature. Fortunately, we not only happen to be in that zone, we also happen to have a very circular orbit that stays in the zone. If our orbit was squished and it was longer and skinnier and not round, we'd go in and out of the zone all the time. But fortunately, we just so happen to stay in the zone all the time. How about this one? Size of the Earth. Too small, you have no atmosphere. The planet has to have so much gravity in order to maintain an atmosphere. Gases, of course, expand, and if they don't have the gravity holding them in, they'll just float off into space. Look at the smaller planets, Mercury and stuff. They have no atmosphere. The moon has no atmosphere. They don't have the gravity to sustain it. Any gases that would accumulate poof out into the outer space, and they're done, and they have no atmosphere. So if Earth was too small, we would all have a very hard time breathing right now because we'd have no atmosphere. Too big, however, and it contains too much atmosphere, and it becomes crushing. Not only just atmospherically speaking, but even just everything becomes too heavy. In other words, what if, instead of being the size that it is, our Earth was, say, 5 times bigger? 5 times bigger, if you currently weigh 150 pounds times 5, you now weigh 650 pounds, if I do my math right. If you weigh 650 pounds, how are you going to go home and eat your lunch? How are you going to pull yourself off the floor? How are you going to move? You can't. And so life becomes very difficult, and there you can read impossible. All right? So you have to have just the right size planet for life to really, especially in terms of human existence, to be just right. And it just so happens that Earth is just right. Yeah, okay. How about this one? Rotational speed and wobble of the Earth. Our days are about 24 hours long. Hypothetically, what would happen if our days were 72 hours long? What would happen? What happens in the morning, and the sun goes up, and by mid-afternoon, about 3 or 4 in the morning, what started out as a 55 or 60 degree day has gone up into the 60s and through the 70s. Now it's in the 80s, possibly 90s if it's summertime, right? The day gets warmer the longer the sun is up. What happened if the sun is up for, say, 36 straight hours? Now, it's the wintertime. The sun goes down, and what happens? The temperature tends to drop. Now, our friends up on the poles know about this because they have extended periods of bright and dark. What happens when it's dark for too long? Heat is radiated off into space. It's not replenished by the Earth's radiation and the heat, and the temperature drops. Everything deep freezes really fast. So how important is it that we have just the right balance, just the right rotational speed of our planet so it doesn't get too hot in the day and too cold at night? Is that pretty important? Yeah, I think that's fairly important, yeah. Or else crops would die either from baking or freezing, or both, depending on what time it is. Yeah, but life wouldn't survive as we know it. Wobble of the earth, again, producing the seasons. What happens if we didn't have that wobble, our seasonal back and forth that we have? One side would always be facing the sun more so than the other. That leaves half of the earth constantly getting hotter and hotter, the other half constantly getting colder and colder. These oceans would get super hot, these oceans would get super cold, this land would get super hot, that gets super cold. And a very narrow band on our planet probably might be livable right in the middle somewhere. But it just so happens that our planet wobbles back and forth. So you get periods of hot, periods of cold, everything mixed, everything matches. Now you have almost a whole planet to live on. Antarctica, maybe not so much. But most of the planet is pretty livable, right? Just so happens it works out that way. Again, just this last week I came across this from nationalgeographic.com online. I assume it's current because I just pulled it off this last week, by Abel Mendez. He says, of the 1,780 confirmed planets beyond our solar system, as many as 16 are located in their star's habitual zone. That's the just far enough away from the sun to be just right zone, where conditions are neither too hot or too cold to support life. I ran the math on this. 16 out of 1,780 comes to 0.9% of them are in the right zone. Now, that doesn't cover all the other factors that we're looking at to make a planet hospitable. That's just where it's located from a star. Again, I saw varying numbers on this, but this was the best one I could find in terms of specifics. Maybe they've found more since, I don't know. But according to these numbers, and it says as many as 16. It sounds like they're not even sure that all of those are. So if that's true, 0.9% of the planets, just by chance, happen to be in this zone. He continues on to say what we just discussed. Size also matters. A planet that's too small can't maintain an atmosphere, and one that's too large will have a crushing atmosphere. Again, it has to be just right to support life. How about this one? A magnetic field keeps us from being destroyed by solar radiation. What would happen if we had no magnetic field around on Earth? We would get blasted by radiation from the sun, and we would die, right? Living things would die. The radiation comes in, it disrupts the cell, it disrupts everything about it, and it can't survive. One of the ways the laboratories will sterilize an area sometimes in hoods and stuff like that where they're working. At the end of the day, everybody goes home and they turn on they turn on UV lights in this little area. And the UV light comes out, it shines on everything, destroys any cellular activity that's going on, any germs are dead. They come back in the next day, turn off the lights, and everything's sterile and ready to go again. What would happen if the Earth wasn't able to block out that radiation? Would be one giant, round, sterilized hood, wouldn't we? Our entire planet would be sterilized. But, coincidentally, we happen to live on a planet with a rotating iron core, if indeed that's what causes it, and we have a nice magnetic field around our planet. Circular orbit, we talked about this already, but we maintain a constant distance from the sun. Too close you cook, too far you freeze, but ours is circular. It works out really nice. Also, circular planetary system in general, all the other planets tend to do the same thing. If we had ours that was even circular and nice and calm, but another one that was constantly interfering with our path, again, sooner or later we'd get kicked out of our orbit and then we would die. And finally, this one, a single moon revolving around once a day. What does that have to do with anything? It drives the tides. It keeps the oceans oxygenated, keeps the currents flowing, keeps everything regulated instead of things getting stagnant and stale and deprived of oxygen. So many factors that go into making a planet hospitable that we don't usually think of, and I guarantee this is not an exhaustive list. These are just things off the top of my head that I looked up. So many things that go into making a planet habitable, and we just happen to be on that planet. We, as life forms that statistically could not have created themselves, happen to have created themselves on a planet that statistically shouldn't be here, in a solar system we can't explain because it's so orderly, and we just happen to be on this planet where we can thrive and survive with all these factors going on. What do you think the odds are? I don't think I can count that high. I think this screams for a little bit of design going on. Are your brains tired yet? We've only looked at a couple small pieces of the universe around us that allows us to survive, what we would call creation. and I think it demands that we start to seek the Creator. There is more. We're going to spend one more week on evidence for God, because I want you to be convinced. I don't want anybody here to go away saying, I'm not sure I've heard enough evidence. So we're going to spend just one more week. Next week, we're going to look at some of the evolutionary evidence that they use to support the evolution, and we're going to see if that holds any validity as well. We do want to be fair and give equal time, do we not? But we're out of time this week, so we'll do that next week. Let's pray and we'll dismiss. Dear God, we thank you for this morning, when we can look not specifically into your word this morning, but at the universe you gave us. Again, you told us in the scriptures that the heavens declare your glory, that the world around us demands that you exist. And once we realize you exist, the next question is, how do we find you and how do we behave in a way that pleases you? But that's for another week. But we thank you that you gave us creation to look at. Thank you that you gave us all the reason in the world, literally speaking, to believe in you. And to not believe in you is beyond silliness. It's self-deception. Thank you for giving us reasons to believe in you and a way to find you. In Jesus' name I pray, amen.